the higher derivatives, the higher order derivatives, the application of derivatives, increasing and decreasing functions, critical numbers, and their use in analyzing a curve or f of x, a function, without the need of graphing it. If there is a peak and extrema point that we will call a critical point, it will act as a peak, maximum or minimum, using the very powerful tool, the first derivative test, and then the absolute extrema. So let's go with the higher derivatives. We know that it arises in applications, the need of higher derivatives, like the famous application of physics. We know that the velocity is the rate of change of the displacement, or the derivative of the displacement, and moreover the acceleration is the rate of change of the velocity, or we might call it the second derivative. So we needed the higher derivative for the displacement. And of course, in other applications, the higher derivatives was enabled people to commute and drive another formulas, and therefore we can find the second derivative now, which we can denote it as y double dash or f double dash, or we might call it double prime of x, which acts as the second derivative. Remember this operator, now it's raised to the power of 2 and applied to the same function f of x. We might say also d squared y by dx squared, and higher derivatives as well. So if we are going to talk in terms of n, any higher derivative, we are going to say that it's f to the n of x. Instead of writing these primes or these commas, we might write a power, but in order to differentiate it from the ordinary power, we are going to enclose it with these brackets. So if we have f of 4 and the power is between brackets, this means that that's the fourth order of the derivative and not to the power of 4. Okay, let's take now some exercises from the worksheet, and the rest of the rate of change for if the distance is its derivative, or its rate of change is the speed. So the speed rate of change is the acceleration, and the acceleration rate of change is called the jerk. The jerk rate of change is called the snap. The snap rate of change is called the crackle, and then the pop. This is the sequence of the physics for the exercises for what the people exercised and commuted. So for worksheet 6, now we already know how to differentiate. So let's take number C, D, and E to discuss again together. In part C, we have here this term minus that term minus the other term. Remember that the minus acts as separator, where we can differentiate each part alone. This needs a rewrite, of course, because of the radical. So the f of x, we need to commute here f triple prime, the f triple prime, the third derivative, for this given f of x. First, let's facilitate it or make it more convenient by rewriting it. The power inside and the power outside, remember when we have x to the power of n raised to the power of m, that was equivalent to x to the power n over m. So we might leave the 4, and x is going to be to the power 3 over 5. And we will have here minus 1 over 8 will be kept as it is as a coefficient, but the x we can take it upwards with changing the sign of the power, minus square root x, which we can write it as x to the power of half. Now for part C, let's commute the f dash from the rewrite that we did for f. Now we have 4 times x to that power. We might drop in the power, so it's going to be 4 times 3 over 5, and the new power of x is what is this 3 over 5 minus 1, which is minus 5. 3 minus 5 is negative 2 over 5. And then minus 1 over 8 is the coefficient that drops if it's multiplied with a function in x. And again, we will differentiate the x to the power of negative 2 by dropping the power negative 2. And the new power will be negative 2 minus 1, which is minus 3. And then minus and drop the half. And x will be to the power half minus 1, which is negative half. Now we might try to rewrite or try to simplify this form for our convenience, because we are going to drive up till the third derivative. So we might say that f dash of x is equal to 4 times 3, which is 12 by 5, and the x is raised to the power of negative 2 over 5. Now we have minus 2 times negative 1 over 8. We might simplify this out to be negative 1 over 4, and x will be to the power as it is negative 3, and then minus half is dropped as it is as well, and the power is negative 1/2. Fine. Now we can drive the second derivative. So let's get f of double prime, which will be, we will drop the power again, so we have 12 over 5 times negative 2 over 5, and the new power is negative 7 over 5. It's the minus 1, minus 5 over 5, and then the other term, minus 1 over 4, will be dropped, the negative 3, which is the power, and x will be minus 3 minus 1, which is minus 4, and then finally the minus half, and the negative 1/2 in the power will drop, and x will be to the power of negative 1/2 minus 1, which is minus 3 over 2. Again, for our convenience, we might rewrite it. We might rewrite it or simplify it while we are getting the derivative, if you are not going to do any mistake, and you will take care. So we might say that this is going to be negative 24 by 25, and x is to the power negative 7 over 5. Combine the 3 and 1 over 4 to be positive 3 over 4. It was going to be here the negative, this was going to be positive, and this is positive, times the negative. Therefore, here negative 2 times negative 1, 8, this is plus 1 over 4. So I will make this plus, and then we will edit that, because it's going to be minus, this is over 5, minus 3 over 4, and x to the power negative 4. This is the second derivative, and then plus, this is the 1/2 times negative, and we have a negative, so it will be positive, yes, 1 over 4, and x to the power negative 3 over 2. That's the second derivative. Let's drive the third out of that form now, f of the 3 prime, 3 dash, or we might rewrite it as f like that, power 3 inside the brackets. The derivative now is going to be exactly the same, where we are going to drop the power we found in the second derivative and subtract 1. It's going to be negative 12 over 5 minus 3 over 4, and we will drop the power, and the new power is negative 5, and then plus 1 over 4 is dropped, and the power, while the new power is x to the power negative 5 over 2, and we do it minus 1. We might leave this like this, because that's the last derivative we need to drive, or we might simplify it to have at the end a simplified form. So rewriting it is going to be 168 by 125, and x to the power negative 12 over 5 plus 3, and x is going to be to the negative 5. This 4 is going with that 4, and the negative times the negative is positive, and then we will have minus 3 over 8. That's the simplest form of x to the power negative 5 over 2, and that's it. Very well. Now let's take number D. So I'll take part D, where we have the root, and we need to commute the second derivative. So we have f of x here, x times square root of 9 minus x. We can call this u and v, like you know, it's times u times v, and we can't algebraically distribute the x. Of course, you know this because of the square root. So we might say that we have u, which is equal to x, and therefore u dash is equal to 1. If v is the 9 minus x of the square root or of the power half, then what is going to be the 1/2, and the 9 minus x as it is with the power half minus 1, which is negative 1/2, times the derivative of the inside, which is negative 1. And then we write for f dash of x or y dash is going to be u as it is times the derivative of v, which is, we can combine this to be negative 1/2 times 9 minus x to the power of negative half. So it's going to be negative 1/2 9 minus x to the power of negative half, and then plus the square root of 9 minus x as it is times the derivative of u, which is 1. Now we are able to find the f double prime, the f double dash. Again, we have here, if we need to rewrite f dash or f prime of x, we might just take this negative half outside. It's going to be negative half times x times 9 minus x inside that bracket. Of course, we can't distribute the negative half inside, neither the x, because of the power of negative half, it forbids that. Plus root 9 minus x. Now we are able to go to commute the second derivative, where we have here x times the root, and this, of course, we might apply again the product rule. This is u and that's v, so it's going to be negative half x, which is u, times the derivative of v, which we will open the bracket, drop the power, and we will have the same bracket with the new power, negative half negative 1, times the derivative of what's inside. 9 is 0 and negative x is negative 1, plus now the 9 minus x all to the power negative half as it is, times the derivative of negative half x, which is negative 1/2, plus the derivative of the square root of 9 minus x. We might see it like that, and we know that the derivative of the root is 1/2 the root times the derivative of what's inside the root, which is negative 1. So you might know that the derivative of the root x is going to be 1/2 root x times 1. What if it's a root of a function? We have said this before. This is like a shortcut. You might use it and you may not like it, so you may ignore it. It will be 1/2 root the function times the derivative of the function. And this is what we applied here. Or you might simply transform this square root into the power of 1/2, and then you will solve it directly. Now let's get the last one, which includes the len. We need to get the f double prime for the given f of x, which is a simple one that includes the exponential and the logarithmic. So let's drive the first derivative for that f of x. Now one might observe that we have len and then x times x squared plus 1, and this is a product inside the len. We remember that we had the property of the len. If there is a product inside, we might simplify it into len x alone and len y alone, and then this product is transferred into what? Into addition. So we might rewrite f of x. This is for your convenience. Again, it's not obligatory. You might just start to derive the derivative from that formula, and it will be correct as well. And then plus the exponential ex squared plus 2x. We won't benefit from separating these powers, so we might leave it like this, and therefore the f dash is going to be the derivative of the len x, yes, it's 1 over x, plus len something, it's 1 over that something, times the derivative of that thing, which is the 2x, and then plus is a separator, so we will get the derivative of that alone, the derivative of the exponential, because we have the function in the power, so we will not drop it and subtract 1 like we do with the numbers, right? The derivative of the exponential is itself times the derivative of the power. Now, the derivative of x power 2 is 2x plus 2x derivative, which is 2, and the 1 derivative, which is 1. Now, that's the f dash. I might rewrite it as well as 1 over x, that's the simplest form, plus we can write this as if this 2x is over 1. We might combine them together to have 2x over x squared plus 1. So the numerator times the numerator and the denominator times the denominator, and then plus 2x plus 2 multiplied with the exponential function. Now let's commute the second derivative. Here we have the derivative of 1 over x. You remember that we said before again that 1 over x derivative directly can be commuted as negative 1 over x squared. If you like or prefer to rewrite it as x to the power of negative 1, it will be the same. You will drop the power to get the derivative, and you will subtract 1 from the minus 1, which will become negative 2, which is exactly the same as the one above. In general as well, we might say if we have 1 over a function in x, which we call usually u, the derivative is going to be negative 1 over u squared times u dash. So here we might directly write negative 1 over x squared, and then we have a quotient rule for that bracket. So we will say over the derivative squared, and then I will copy the derivative upwards, times the derivative of the numerator. The numerator is 2x. So the derivative is 2. And then we subtract, this is what's significant about the division rule, the first, or the numerator as it is, times the derivative of the denominator, which is 2x. That's it. And then here we have a product rule, right? And the space won't save. So let's take it. Let's take the derivative. Let's call this, for example, hash tag, and then the derivative of the hash is what? If this is, we might rewrite it also 2x plus 2, and then the e, the exponential function, and we are getting the derivative or the dash of that function. Here we have a function time another function, so we will call them u times v. The derivative of the products is the first as it is, times the derivative of the second. Here the function is in the power, yes, that's the exponential that we have just did before, e to the power of the function as it is, or itself, times the derivative of the power, and then plus, now the v as it is, times the derivative of the first, which is the u, which is 2. Very well. So this is supposed to be written there, and we might just take it and put it here with an arrow in order to save our time. Okay, very well. So this is about the higher derivatives that's required. Now we need to use the derivative. Let's recall some information before going through that exercise about the derivative and its relation with the behavior of the function, how we are going to make use of this, or how the mathematicians made use of that, and we are going to follow. So we know that the f dash by definition is the instantaneous rate of change of the f of x with respect to x. And geometrically, we said that it's in the same time is equivalent to the slope of the tangent line to f of x at a certain instant of x, or at x equals a. So we know that we might have a function, this is the xy plane, we might have a function that looks like this, for example, this is f of x, and if at x equals a at a certain instant, at x equals a, we got a tangent line to that function. So the slope of that tangent line, is going to be equal to the derivative of that function at this point, at that instant of x, right? Okay, this is very well. We did this many times before the midterms and in the previous worksheets. Now, how many lines can we have? How many possible lines can we have? We might have a line like this if it's of a positive slope. So we will say if the line is with a positive slope, that mt, which is equivalent to the f dash of a, is bigger than 0, which means that it's positive. Right? So if that slope is positive, if this mt or that slope is positive, it follows the right sign like we said before when we were describing and discussing the linear models. This means that the f of x is doing what? If the slope is positive, the f of x will be increasing. Like here, it's a direct change. As x is increasing, y is increasing as well. So we will say that f of x, we can conclude that it's going to be increasing. Very well. Let's consider another situation. Here, this function is of a different shape, and we have a tangent line as well. This tangent line is falling, right? When x is increasing, the y is decreasing. And we call it as if it's falling from a mountain or something, and this value is going to be negative, less than 0. And what does that tell about the function itself, the curve f of x? If the slope of the tangent line is negative, then f of x must be decreasing. So we might conclude that the f of x is decreasing, and of course this would help us a lot in analyzing any function. Now we don't have to graph it, we will just get the derivative and discuss the sign of the derivative, test its sign, and then we will know what does the function do in such an interval. Okay, let's take another situation. Now consider that the f of x got some peaks. So we have a peak here and we have a peak there. If we were able to take a tangent line from this point, which we might call it negative a, it's in the negative side, if this is the y coordinate, and if this is another value which we might call b. So if we took a tangent line at b where we have a minimum peak, the f of x is the pink curve. So this is the f of x, there is a maximum peak here and there is a minimum peak there. The tangent line is going to be horizontal, and in this case we know that the slope, which is equivalent to the f dash at the same instant, which is negative a here, or the b, is equals to what? Is equals to 0, because it's horizontal, so it doesn't have a change in y, so it's 0 over a change in x, which is 0. And if this is 0, we can conclude that the f of x has what? It means that f of x has a peak, whether maximum or minimum. So they say that f of x, they call it suffers a peak, or a change in the behavior, whether it was increasing followed by decrease, or it was decreasing followed by increase. So this point will act as relatively, it will be a relative What type of peak? If the function is increasing and then decreasing, so it's a relative maximum peak. And if the function is decreasing followed by increasing, it's going to be a relative minimum peak. So it's going to be a relative minimum. Sometimes they call it local minimum because it's minimum locally or relatively to the points surrounding it. Here again, we might call it local maximum as well. So these are the two types of peaks that we have. And let's consider the last scenario. So imagine that we have an f of x like that gray curve or a g of x like that gray curve. At that instant x equals a, the tangent line, which is equivalent to f dash at a and equivalent to g dash of a, is of what slope? Its slope is undefined. You remember that the vertical lines, we said they have no slope. They got no slope. And in that case, we will say that f of x also suffers a change of behavior, but in a sharp way, not in a smooth way like the other one. So if the function is increasing and then decreasing, but in that way, if we took a tangent line to the point at that peak, this tangent line, in order to touch the curve, is going to be vertical line, right? And in this case, we will say that the f of x is having either a relative maximum or a relative minimum, right? So based on this discussion, let's conclude the following, which tells us a lot, of course. So if we know the f of x in general, how can we analyze it? If we are given the f of x, we will get its derivative, f dash, and then we will test intervals around critical points. Okay. Around critical points. What are the critical points? Now we knew that the critical points can be derived from two situations. Whether we have the tangent line is equal to 0 to the curve at that point or is undefined. So this is exactly the definition of the critical points, where we are going to have this f dash that we derived once equal to 0 in order to get the critical points. We will solve f dash of x equals 0 once, or if we have a fraction, we will be able to solve it undefined. Okay, and these two steps is going to commute the critical points. We will have over the number line to apply the first derivative test. Then we will be ready to apply the first derivative test, which is on the number line, testing the function using the f dash of x, which is the first derivative, around the critical points that we might call x1 and x2. And according to f dash, we are going to test each interval. And we are going to test, for example, interval 1 by test point 1, and interval 2 by test point 2, interval 3 by test point 3, and hence, according to the f dash of t1 and f dash of t2, according to the sign, we are going to conclude what would happen in the f. So if f of t1 is increasing or is positive, we will say that indicate the positive. If f dash of t became negative, we will indicate the negative throughout the whole interval. If f of t3 is positive, we will indicate that with positive during the whole interval, and therefore we can expect the f behavior. If f dash, which is the slope of the tangent line, is positive, it means that the f, the function, was increasing, right, up till the x1, and then it starts to decrease up till the x2, and then it started to increase again. So this is what we know about the function from just the sign of the f dash at these testing points. And also we might include that x1 might be called, and its corresponding y is a relative maximum, which we call it an extrema point. And extrema is the plural, so it's an extreme or a peak. And the x2 with the f of x2, how was the behavior around x2? The function was decreasing, then increasing. So of course we have reached a minimum peak, so we will call it a relative minimum or an extreme as well, but its type is minimum, or we might call it a peak point. But what we will use is the relative maximum or the local maximum. Relative or local. Okay, which means that there is an extreme or there is a peak. So this is an equivalent formula. So we know now the increasing interval, the decreasing interval, and the maximum and minimum peak if it exists. There's something I did that some of you noticed and some of you didn't, that we have commuted the f of x1 and the f of x2, because there is a very important condition for the critical points that they must belong to the domain of the function. So if the corresponding y was not possible, got an error in the calculator while you're commuting it, or got like an undefined value, we will not consider it as a relative maximum nor relative minimum, because it makes sense, because the point doesn't exist in the function from the beginning. So how it can act as a positive or as a maximum or minimum? So we do this condition by commuting the corresponding y. If there exists a corresponding y, then we call it a relative minimum. If the critical point didn't have, like we will see in the exercises, and we will say that the increasing and decreasing intervals also can be commuted. We don't know from where here it started to increase, so we will say from negative infinity up till x1. Make sure that this interval is of open brackets. These values are not considered, and the function is what? F of x is increasing, and then from x1 to x2, again open bracket, the f of x is what? Decreasing, and then from x2 to infinity, because we don't know till where, so we will say till infinity, the f of x is what? Is increasing. So now we are able to discuss the whole behavior of the function. Now exercise 2 says show that the function f of x equals x squared is decreasing on the interval, on that interval. So we know that x squared is a parabola U shape that is formed with a symmetry along the origin or around the origin. So before the zero, of negative infinity to 0, this function is decreasing. Of course we know that it's decreasing, and from 0 to infinity it's increasing. Of course we know that it's increasing. We need to use the derivative to show this. So simply we are given the critical point as in here ready, right, which is equal to 0. We are given the critical point which is equal to 0, where the function is changing its behavior around. So we will simply get the derivative, the f dash, for the x squared, which will be 2x, and then test the interval and say at the interval from negative infinity to 0, and this bracket is exactly the same as the opened square bracket. So you might use this bracket or that one. It indicates the opened interval. So in this interval, we know that f dash, we might choose any point in this interval, like negative 3, for example, is going to be negative. Or what's important is the sign. So f dash at negative 3, that's the slope of the tangent line, is negative. You remember when the slope of the tangent line was negative, this indicated that f of x is what? Is decreasing. Therefore, we conclude that the f of x is decreasing. Very well. And at the other interval, which is from 0 to infinity, the f dash, let's pick any point for example 100, is equal to be what? We don't need the exact equal, we need the sign. It's going to be positive bigger than 0. Therefore, we conclude that f of x is what? Is increasing. Yes. Okay. Very well. Let's take the next exercise using the first derivative test to find the increasing, decreasing intervals and find all the relative extrema local of the function. So here we need to do this with part B. First, of course, we are going to get the derivative. So commute the f dash. Here the derivative of, we have minus and plus in between, so they act as separators. We will drop the 4 to have 12 and x to the power of 3, and then minus, drop the 3 beside the 4, it's going to be 12 and x to the power of 2, minus, drop the 2 beside the 12, it's going to be 24x, and the derivative of the 5 by itself is 0. Now what do? We are going to use either f dash is equal to 0 or f dash is equal to undefined, right? And what do we do? What do we have here? Actually, we might equate this by 0, and we don't have a denominator. You know that we can do this f dash equals 0 if it's 0 divided any number. This is equal to 0. So if we have a fraction, we will equate the numerator with a 0 regardless the denominator. Here we don't have a denominator, so we will directly equivalent or equate the f dash with the 0. For the undefined, divide by 0. This is the undefined, or what we knew from the limits as infinity. So any number divided by 0 is an error or undefined value. So this is how we are going to commute it. If f dash is a fraction, we have a numerator and denominator, we will equate the denominator by 0 like we will do later on. Now let's continue solving this for 0. Of course, we might note that we have an x in the 3 terms. So for solving f dash of x equals 0, we might take an x as a common factor and the 12 as well. So we will be left with the x squared minus x, right? We take the 12x from here and then minus 2, and we have taken the x equals 0, and this either 12x times this bracket is equal to 0. This means that either 12x is equal to 0 or the x squared minus x minus 2 is equal to 0. If 12x is equal to 0, this means that x is equal to 0, or solving this, we are going to have, by the calculator also, we are going to have negative and positive is equal to 0. So either x is negative 1 or x is equal to 2. Now, how many points do we have now? We have x equals 0 or x equal negative 1 or x equal 2. These are the solution that we got from solving f dash equals 0. So now, after commuting the critical points, these were the critical points, we are ready to go for the first derivative test and apply our test. So we are going to apply the first derivative test over the number line. We are going to locate these points. We know that the number line runs from negative infinity to infinity, and we are going to test in f dash. This is in order not to forget it. And we are going to locate the negative 1, the 0, and the 2. Now we have divided the number line into how many intervals? We know that we have now n plus 1 intervals. These are 3 points, so we have 4 intervals. From negative infinity to negative 1, as we decided it's going to be opened, always opened interval, and from negative 1 to 0, and from 0 to 2, and finally from 2 to infinity. Let's pick a point in the first interval. we might call it -2. So if x is equal to -2, what's the f dash of -2? We might go to this f dash that we commuted, and we will get the sign. So it's going to be negative. So we will indicate this as negative on the number line. Here, let's pick a point in this interval from -1 to 0. Oh, this is very tiny. Let's get x equals -0.5 or -0.1 or -0.9. Any point before the -1 and after the 0. So f dash at that point is going to be positive. So we will indicate this in the interval. Now from 0 to 2, we might pick x equals 1. And in that case, f dash of 1 is going to be negative. -1 here, it's going to be 1, sorry. It's going to be 1 minus 1, which is -2, minus 2 is -4, times 1, which is going to be positive. And then, sorry, this is negative times positive is going to be negative. So this means that we have a negative interval, and after the 2 we might pick at x equals 5 or x equals 10. So f dash of 10 is going to be positive number. 100 minus 10 minus 2, this is a positive number, times 10 times 12, this is a positive number. So we will indicate the whole interval as positive. Now we know that if f dash is negative, this meant that the function f of x is what? Yes, decreasing. And if it's positive, it means increasing. I might write it like this, decreasing and then increasing. This is the f of x. And if it's negative, again, it's decreasing. And if it's positive, so again, it turns to increase. So here we have a decreasing interval and an increasing interval. The last thing is to indicate the local maximum or local minimum. So we will commute the f of -1, and the f of -1 is equal to 0. So we might say that at -1 and 0, this is the complete point coordinate or pairs, the function was decreasing and then increasing. The function was decreasing and then increasing. So of course this was a local or a relative minimum. Okay, and then f of 0, we will return to the function itself. This is going to be 5, and we will say that the 0 and the 5, because the function around the 0, it was increasing and then decreasing, so we will say that it was a relative maximum. We don't have to write or indicate what's happening to the function. This is just for our discussion. You might just write at f of 2. F of 2 is going to be -27. So this means that the point 2 and -27, because the function was decreasing and then increasing, so it's a relative minimum directly. Okay, so now we made a full analysis for the function from the derivative using the first derivative test. First of all, what we did, we got the f dash, and then we equated by 0, getting the critical points, and then we were able to go to the first derivative test. So we will say that there are 3 main steps. Let's repeat this with different situations in different functions. So for part D, we are going to get the derivative again, f dash of x, which is equal to what? That's a quotient rule. So we will take the denominator, we have u over v, we will take the v squared, and then we will repeat the v without getting any derivatives. Now we will differentiate the numerator minus the numerator without differentiation times the derivative of v, which is the denominator. You remember when we said that if the question says or asked to commute the f dash, we stop without simplifying. Now we need to solve this function for f dash. So it's from our benefit, we might try to rewrite it if it's possible only. Of course, we might distribute that term, for example, here and there, and this will give us the 2x cubed minus 9 times 2, which is 18x, and then minus multiply these two terms together, we will have 2x cubed over the same denominator, power of 2. And of course, we notice that we might simplify out these two together in order to have negative 18x over the x squared minus 9 all squared. And of course, this is for our benefit. We need to solve now. F dash of x equals 0, and this comes from the numerator. If negative 18x is equal to 0, this means that we have 0 divided whatever, which in this time is going to be 0. And this means that x is equal to 0, and then f dash of x is undefined. This is the other case that we need to consider, and this means that we need the denominator to be 0, whatever the numerator is. Of course, not whatever, but for our cases, whatever the numerator is, if the denominator is 0, then it's undefined. So solving this equal to 0, of course, we would apply the root on both sides, and then we will be left with x squared minus 9 equals 0, which means that x squared is equal to 9, and this means that x is equal to positive and negative 3. Now we have the critical points as 0, negative 3, and 3. We might test the corresponding y here in this stage, and we might go to the first derivative test directly. However, we will always test around them, around the critical points, all the critical points, whether they are in the function or not. That's why we might take them to the first derivative test first in the number line, and we locate the points negative 3, 0, and 3. We test in the f prime or in the f dash. Now let's take the first interval where we have it from nowhere, which we can call it negative 3, negative infinity. So it's from negative infinity to negative 3, again opened interval, and then from negative 3 to 0, and then from 0 to 3, and finally from 3 to infinity. The point that we might pick here after the negative 3, which might be negative 4, right? So f dash of negative 4 is going to be what? It's going to be positive, greater than 0. So it's going to be positive, this interval, which means that the f of x is what? If f dash is positive, it means that it's increasing. So the f here is increasing. Let's pick a point from negative 3 to 0. For example, it's at negative 1. So f dash at negative 1 is what? It's positive again. So it means that the function is increasing. We will indicate the positive in the number line, and we might indicate the arrow. The arrow is not very important, but the positives here are important. Now we will pick a point from 0 to 3. Let's say of 1, and f dash of 1 is going to be negative, which means that f is decreasing. Indicate the negative here and the decreasing for ourselves. Here we have f dash of any point after the 3, that might be 5 or whatever. It's going to be negative again, which means that the function is decreasing, and we indicate the negative here. Now we know that where the function increase and decrease, and we have now calculated the increasing and decreasing intervals. So I might call this an increasing interval, this is a decreasing interval, and so on. These are the intervals of increase and decrease. And finally, we can commute also the relative or the local maximum and minimum, or what we call the local extrema. First, we will commute f of -3, f of 0, and f of 3. F of -3 is going to be, I'm going to commute it at f. So here only 0, which got the corresponding y as 0. So the point 0 and 0, we will go to see the behavior of the function around it. Before it was increasing and then decreasing. So of course we have reached a maximum peak. So you will call this a relative or a local maximum extreme, right? The function at -3 and 3 got divided by 0, so it was undefined or gave you an error in the calculator, and this means that this point doesn't exist in the function itself, so we can't call it negative or positive. Also, before it and after it, it was positive. Before it positive increasing and after it positive increasing, so it wasn't a peak from the beginning. But what made us to decide that it's not a critical point for this function because it's undefined or doesn't exist inside the function. Let's pick number G. Now what do we need to do? We need to do exactly the same requirement. We need to find f dash, which is, we have here the root. Of course, we might rewrite it as x to the power of what? 1 over 3, the power inside over the power outside, minus x. And then we will have as a derivative, the 1 over 3 is going to be dropped, and the new power 1 minus 3 is going to be -2 over 3 minus 1, which means that we have x to the power -2 over 3 minus 1. We need now to equate this by 0, and we know that if we have a negative power, it was in the origin in the denominator. So this was x to the power 1 over x to the power 2 over 3 minus 1. So we have a denominator, but a denominator minus 1 doesn't look so good. So we might rewrite it in one denominator, x to the power 2 over 3 post, and then we do that cross. So we have here 1 minus, it's nothing here, so we will see it as if it's 1. 1 times 1 is 1, and then x power 2 over 3 times 1, it's going to be minus x to the power 2 over 3. Now we have one fraction, so we might go with the denominator alone, and we can solve f dash is equal to 0, and in this case we are going to take the numerator, equate it with 0, so take the x to the power 2 over 3 to the other side. Of course, we will apply the power of 3 first to get rid of the radical or the fraction in the power, and therefore we will be left with x squared. This is equals to 1, right? We moved this x, right? And we have 1 inside here, not 0. Okay, so x squared is equal to 1, and if x squared is equal to 1, this means that x is positive or negative 1. Okay, let's go now for f dash is undefined because we have a fraction, and we might take the numerator as it is equal to 0, and this means that x is equal to 0. So we have how many critical points here? We will go to the first derivative test and locate the 3 points that we got and test in f dash in between them from negative infinity to infinity. The points are -1, 0, and +1. So the first interval is from negative infinity to negative 1, and then from negative 1 to 0, and then from 0 to 1, and finally from 1 to infinity. Let's pick a point in the first interval. It can be negative 2. So f dash at negative 2 is going to be negative, indicating a negative sign here, which means that the function is what? Decreasing interval. And then we pick a point in the second interval from negative 1 to 0, from 0 to negative 1. Let's pick negative 0.5, which is going to be bigger than 0, which indicates here positive in that interval, and the function is increasing in that interval. Finally, before the last interval from 0 to 1, let's pick 0.5, and at 0.5 the function is going to be increasing as well. So we are going to have an increasing interval, and then the f dash at any point before the 1, after the 1, which is going to be, it will give us negative f dash. We substitute at f dash. Of course, you might substitute here or here or here. Any formula of these, the most convenient for you. If you're going to use the calculator, so the first one is okay, or the second one if you're going to use your mind. If it's negative, this indicates a decreasing interval. And then we have here what? A negative sign. From 0 to 1 it was increasing, positive, and from 1 to infinity is negative, and therefore we might go to commute the corresponding f of negative 1, f of 0, and f of 1. So here f of negative 1 is going to be negative 2, so we substitute x by negative 1 here. The cubic root of negative 1 is negative 1 times 3, this is negative 3. Negative 3 plus 1 is negative 2. At 0 it's going to be 0, and at 1 it's going to be 3 minus 1, which is 2. So we have here at negative 1 and negative 2 a relative, and at 0 and 0 a relative peak as well, and at 1 and 2 a relative peak as well. What's the type now? We know that before the negative 1 the function was decreasing and then increasing, so it seems that we were at the bottom of a hill, so that was a relative minimum. And at 0 before it was increasing and then increasing, so it's not a critical point. And of course f dash of 0 is undefined, so this is neither nor. So it's not a relative, it's neither nor, because although it's inside the function and it's defined in the domain of the function, because its corresponding y is well defined 0, but its type is neither nor. Finally, at 1 and 2, the function was increasing and then decreasing, so it was a relative maximum peak. Okay, very well. So now we have commuted everything for that part. Here we will do the same thing for part E. So we will get the f dash. We are going to make this more quickly now, because now we know it. We have x power 2 times the square root, so we will apply the product rule, u times v. It's going to be first derivative second, which is half 3 minus x to the power of negative half times the derivative of what's inside plus the 3 minus x inside the root as it is times the derivative of x squared, which is 2x. And if we have a negative power, this means that we need to drop that. So we have here negative 1, 2, and x squared. So we're going to write it negative x squared. And in the denominator, we have 2. And this bracket with the negative power, we might take it in the denominator to be with a positive power, right? Plus the 2x times the square root of 3 minus x. Now we have something plus another thing. We have a fraction plus a line, or a function which is at a line. And in this case, we need to rewrite it in the form of one fraction. So what we accept of f dash, it's either a fraction or in one line. So we will have a one denominator, which we call it a common denominator, and then we will have the negative x squared as it is, and plus we will multiply this with that, so it's going to be 4x, and the root times the root is going to be cancelled. It's going to be 3 minus x. So this is an algebraic operation that we might do by any method that you are used to. And then we have now f dash as a fraction, something, one numerator and one denominator. So if we need to solve f dash equals 0, we will take the numerator equal to 0. If we need to solve f dash equals undefined, we will take the denominator equal to 0. So f dash can be as a one fraction or can be written in one line. So we directly go to equated by 0, equating that equation by 0. If we have a fraction, we can't have a combination between both. We have to turn it into one fraction. So here we will take, if f dash is equal to 0, and I will take the numerator, negative x squared, and we might distribute here and there this 4x. So we are going to have positive 12x minus 4x squared. We might combine the x squared together. So we'll have the 12x minus 5x squared, and this is the numerator, which we will equate it by 0. We might take the x common factor, and then we will be left with 12 minus 5x here equal to 0, which means that it's either x is equal to 0 or x is equal to 12 over 5, right? And then we will take the f dash equals undefined still, and this will be taking the denominator, the 2 times 3 minus x all to the power of half equals 0. And of course, what we are going to do here, we are going to square both sides to get rid of that half. So we are going to have 4 times 3 minus x equals 0, which means that we have here x equals, let's here divide by 2 first in order to simplify it. So we are going to have the 3 minus x to the power of half equals 0 divided 2, which is 0, and simply then we will have x to the power of 1/2 equals to 3. And now we can square both sides to have x equals the 3 squared. Now, is this function is going, or this f dash that we commuted is going to be undefined only when x is equal to 9? We have a root here, and we know that we have a condition that if we have the root of 3 minus x to the power of half, okay, so here it's squaring it is going to be x minus, okay, let's correct this part here for the value of x, and then we will consider the other section. So we have here this applying the squaring, we will have the 3 minus x power half, and then squared equals 0 squared, and this means that we have a bracket here, so it means that we have 3 minus x equals 0, and then x is equal to 3. Now, is it only x equals 3 that's going to make this f dash undefined? We know that if we have the 3 minus x under the root, if we have any value for the 3 minus x which is negative, is going to make this undefined, or it's going to give us the error. So we will solve this inequality to have x bigger than 3. Take the negative x to the other side. it will have the opened inequality, so x is bigger than 3. So if x is bigger than 3, this f dash is going to be undefined. So in the number line, we might indicate this. We have now the 0. And of course, we need to discuss the f dash behavior around these points. So we will start with the interval from -infinity to 0, where we will pick x equals -1 and then commute the f dash at the -1, which is going to be negative. And then from 0 to 12 over 5, we will pick any point in between. Let's see if it's the 12 divide 5, it's going to be 2.4. So we might pick like 2.5 in order to be before the 5 as well. So f dash at 2.5, it's going to be positive from 0 to 12.5. And then from the 12 over 5 to the 3, we are going to test, for example, at x equals, if 12 divided 5 is 2.4, we might test it at 2.9 before the 3, and therefore the f dash of the 2.9 is going to be negative, so indicating negative here. Now if we tried to have any point in the last interval from 3 to infinity, we will notice that the function does not exist. So from 3 to infinity here, choosing any point equal 4, 5, 6, and even 3.1, this is going to give us f dash is undefined. And we needed to solve for the f dash undefined. So the function here doesn't exist from the beginning if we noticed that f of x include a square root, and therefore there were a condition for the possible inputs or the possible x values. We know that if we have a square root, so the possible x values has to keep what's inside the radical positive, bigger than or equal, because we don't have a fraction. So it means that if we take the negative x by the opposite sign to the other side, it will have the closed inequality, so it's less than or equal what? 3. So that was the possible values of x. This was the domain of the function, or the possible values of x. What we commuted also assure this, or so whether we noticed it from the beginning or we didn't, our analysis went through it, and we found that for different values of x, the f dash was undefined or didn't exist, and therefore we will say that this interval, this function doesn't increase nor decrease, because we were not able to see this through the first derivative test. So we will say directly the function doesn't exist there. And we knew this from the domain of the f as well, which indicated that x got to be less than or equal to 3. So now, this is about the intervals. If it's negative, then it's decreasing interval, and it's negative here as well, so it's a decreasing interval. And we might say that the decreasing interval is from -infinity to 0, union from the 12 over 5 to 3, and then the increasing interval is the left one, and you might do it like this in details. And finally we need to test the f at 0, the f at the 12 over 5, and the f at 3. The f at 0 is going to be 0, and the f at the 12.5 is going to be approximately 4.46, and it's equal to 0 because we have 3 minus 3, which is 0, and therefore before the 0 the function was decreasing followed by increase, so this was a relative minimum, and here the function was increasing followed by decrease, so this was a relative maximum. Here the 0 the function was decreasing, and then we don't know, the function does not exist. So after the 3 the function does not exist. We better not to indicate it as a critical point, although if we have more information we might say that it's local minimum, right? Because it might be that the function stopped at 3, but it still can be like an asymptotic behavior where the function keeps decreasing without limits, and we don't have enough information to indicate this, and therefore we will say that at x equals 3 we don't know. There is no critical, relative, nor maximum nor minimum point. So we will say that we have only relative minimum at x equals 0 and the corresponding y, and we have a relative maximum at the x12/5 and its corresponding y. Okay, that's it. So now here we got the derivative for part h. We got the derivative, it was len of u. We know that the len of u, the derivative of the len of u is 1 over u times u dash, right? So what we did here is we took 1 over the argument or the input times its derivative, drop the 3 to be x to the power of 2, and the 3 will cancel the 1 over 3, minus 4x derivative, which is 4. And then we combine both, we imagine this over 1, and we multiply the numerator with the numerator and the denominator with the denominator. Now we will equate the f dash equals 0, and we will take the x squared minus 4 equals 0, and this will give us x equals positive and negative 2. And then we will take f dash equals undefined, and this will give us the 1 over 3 x power 3 minus 4x equals 0, where we can take an x as a common factor and be left with 1 over 3x squared minus 4 equal to 0. So it's either x is equal to 0 or x squared is equal to 4 times 3, which is 12. So x is equal to positive or negative the square root over 12, which is approximated by 3.46. And therefore now we have the critical points and we are ready to go to the first derivative test. Locating these points over the number line, we have now the negative 2, the positive 2, the 0. So we have the 0 here. We have the negative 2 and the positive 2. We have the square root of 12, which is 3 point something, and the negative square root of 12. We will indicate the behavior of the function first from negative infinity to negative root 12. We will pick a point in this interval. Let's pick f dash at negative 4. So f dash at negative 4 is going to be before it's going to be negative, which means that we have a negative sign here. From the negative square root 12 to negative 2, we have f dash positive. We might try the negative 2.1. We will have it positive, bigger than 0, and then we will take the interval from negative 2 to 0, open the interval as well, the f dash, and let's decide it at negative 1, for example, negative 1, and in this case from negative 2 to 0 it's going to be decreasing, so it's less than 0. and then from 0 to 2, f dash at 1, for example, from 0 to 2 it's going to be increasing, so positive, and then finally from 2 to the square root of 12, still we might pick a point in this interval like 2.5. So f dash at 2.5 is going to be from 2, it's going to be decreasing less than 0, and finally from the square root of 12 to infinity, let's pick a point that can be 4 or 3.9. If this is 3.4, so we might pick 3.9, and in this interval the value is positive, which means increasing. And of course, if f dash is negative, this means a decreasing interval. If it's positive, so we have here a decreasing interval as well, and a decreasing interval, we might write them at once after the number line here. We might say that we have decreasing interval from negative infinity to negative square root of 12, union from negative 2 to 0, union from 2 to square root of 12, and then we have an increasing interval where the f dash is positive, here as well an increasing interval. And finally we need to test the function at these points, the negative square root of 12. This is the simplest way we can do. Another thing you can do is that you can test the domain of the function at the beginning. You might get the domain and then accept the critical points that belongs to the domain of the function and reject the critical points which doesn't belong to the domain of the function. But you have to apply the derivative, the first derivative test around all of the points, whether it belongs to the domain or doesn't belong. So here at negative 12, this function is undefined, so we have an error in calculating the corresponding y. At 2 and at 0, it's undefined as well, and as well as at 2 and at the square root. So all these values are undefined except at negative 2, and therefore only the negative 2 that we can consider as a critical point with its corresponding y, the length 16 over 3. If you need to know the length of the 16 divided by 3, it's approximately 1.67, but we don't need to know this. We just need to know that it's defined and there is a corresponding y for that x, and we will return to the function to see what happened around the negative 2. If we have a change of behavior, then it will act as a critical extreme. Here we have the function was increasing and then decreasing, so it seems that we had a relative or a local maximum. If the function was increasing followed by increasing, it will be called neither nor. If it was decreasing followed by decreasing, it was going to be neither nor as well, although it got a y corresponding y. But if there were no change of behavior around negative 2, we will say that it's neither nor as well. Let's simply take number f. This is going to be a simple exercise. So here, let's get the f dash like we are used. We have the cube root, so we will drop the 1 over 3, and x is going to be 1 minus 3, which is negative 2 over 3, plus 1 derivative, which is 0. So we will say that we have 1 over 3 and take that negative exponent to the denominator. Now we have f dash as one fraction, we accept this. And we say that if f dash is equal to 0, we will equate 1, the numerator, by 0. This is a false statement, so we have no x values. Simply, and then take the f dash equals undefined, and in this case we will take the 3x to the power 2 over 3 equals 0. Of course we will divide by 3 both sides and then raise to the power of 3 and then take the square root, and all this will keep x equals to 0. So we have only one single critical point. Let's go to the first derivative test. Locate the 0 in between the infinity and the negative infinity, testing the f dash of x before and after. So before it, it's going to be positive if we took the f dash here of negative 1, for example, and then we take the f dash of 1, it's going to be negative. No, it's positive as well. So we don't have a change of behavior around the x equals 0. We will say that the 0 and its corresponding, the f of 0 here is the cube root of 0, which is 0 plus 1, so it's 1. So this point is neither nor. It's neither maximum nor minimum, but we know that from negative infinity to 0, the function is what is increasing. So we might say union from 0 to infinity, because both were increasing intervals for f of x. Now consider that we have this f of x as given and that we know its graph. From this graph we might say that we have an increasing intervals from a to x1 and union from x2 to x3. Union, also the function is increasing from x4 to the b. All these intervals are increasing intervals. And the function is decreasing from x1 to x2, union from x3 to x4, union, that's the last interval where the function is decreasing, so we don't have another thing, so we will say it's only decreasing interval. Very well. Also, we can say that x1 and its corresponding f, because this point seems to be located and defined in the function, and the x3 and its corresponding y, and as well the b and the f of b are local or relative maximum peaks, right? And at x equal a and its corresponding value or height, and at x2 and its corresponding height, and at x4 and its corresponding height, what do we have? We have local minimum. Okay, so now we have local or relative maximum and minimum. We need to introduce another expression, which is the absolute. We might say that we have an absolute maximum, at which point this is going to be the highest height or the tallest height, and the absolute minimum is going to be the lowest or the shortest height. So we will say the absolute maximum or the tallest height is going to be x1 or no x at x equals b, right? So at b and f of b, we have the absolute maximum point with the absolute value of the function, and the minimum, it's at x4 at a. The function doesn't exist before the a, yes, but where the function exists after the a, this point is a relative minimum. Also here at this boundary point, the function is relatively maximum at this point relative to the surrounding. The lowest height happens at x2, so we will say at x2 and its corresponding f or y, we will have the absolute minimum and absolute maximum. Like you have noticed now, we need to know the critical points where we will indicate as maximum or minimum, and it's not important as well. What's important is the height. We need the highest or the tallest height and the lowest height. How do we read the height? We directly go to the function and measure its corresponding y coordinate to know the maximum height and the minimum height. So this is measured by the f of x. So for our next critical type of points, which we will call the absolute maximum or minimum, we will need to discuss the height of the function. And let's do this with the one that includes exponential. So at number C, part C, we need to know the critical points, and therefore we are going to get the derivative of part C, e to the power of function. So it's an exponential, it's going to be derivative of itself times the derivative of the function. X power 3 is 3x squared minus 4x minus 7, and this is equal to what? In the next step we are going to equate this by 0, and if we have something times another thing equal to 0, this means that its exponential is equal to 0, or that is equal to 0. And of course the exponential function can't be equal to 0, or it doesn't output the 0. So the 0 comes from this function, where we have in part C, we will have x is equal to -1. If we will have the x and 3x, and then we will have here -7 and +1, which means that x is equal to, or x is equal to 7/3. And these are the only critical points that we have. We will go to locate them over the number line. We need here, what's required is to find the absolute extrema, and it's the absolute extreme or the absolute maximum or minimum. It holds for both. So the extrema is a plural word, its singular is extreme. So it's whether we have a maximum extreme or a minimum extreme. So what we are going to do, we will just go to test the heights. The height at -1, the height at 7/3, these are the critical points, right? Without knowing whether it's local maximum or local minimum, we don't need this. And we will take the boundaries as well. The boundaries of number C is the -1/2 and the 5/2. So at let me commute this. So now we commuted the function at 7/3, which has this corresponding value, and f of -1/2, and at 5/2. At -1/2 it got the highest height or the tallest height. So we will say at the -1/2 and this point we have the absolute maximum, and we got an absolute minimum at 7/3, so this is the absolute minimum. For the -1, because it's not included in the interval of our interest from -0.5 to 5/2, which is 2.5. So from -0.5, here, from -0.5 to the 2.5, it doesn't exist, the -1. Therefore, we will ignore it at this point. Very well. Let's solve number D. We will get the first derivative, and we will find that it's 12x squared minus 6x plus 9. Solving this equal to 0 in order to get the critical points, f dash, we will get no real solutions. So if we try to do this in the calculator, you will get values that holds the letter E, and this means that it's not a real value, and hence we ignore the roots. But what we have here, we do have the boundaries. So we will test the function at the boundaries, f of -2 and f of 1. We will find that f at -2 is equal to -50, and f at 1 is equal to the 22. This is the tallest height that we have, right? So we will call it the absolute maximum for the interval, and this is the lowest or the least height, so we will call it the absolute minimum. Okay, let's take part B. So again, here the required is to find the absolute extrema, which is the absolute extremes, absolute minimum or maximum. And what we are going to do here is to find, first of all, the f dash, and here we have 3x squared minus 12x plus 9, and then we equate it by 0 in order to get the critical points. We have here x is equal to 1 or x is equal to 2, and both does belong to the interval from 1 to 8, which is given. So we will commute the function at 1 and the function at 2, as well as at the boundaries. One of the boundaries was 1, so we will not commute it again, of course. And of 8, the function at 1 turned to be -4, substituting for x equal 2. For 8 it was 192. Here the function at x equals 2 is going to be 10, and therefore we will pick the highest tall, which is at 8. So we will say that the 8 and the 192, this coordinate point, act as the absolute maximum, while at x equal 2, here we have at 1. So at 1 is the absolute minimum, because we got the corresponding height of -4, so this is the absolute minimum. Okay, you will find at the solution that it's commuted at x equal 3. Okay, I checked it now, so we might correct this. X is equal to 3, and of course the corresponding will be something else. Okay, let's correct this with the white. So f of here x is equal to 1 or x is equal to 3. It was a typo, sorry. So it's f of 3. If we commuted f of 3, it's going to be -8, and this is of a lower height. So when x is 3 and y is -8, this means that we have here the absolute minimum. So it turned the situation to have the absolute minimum at the point 3 and -8. Very well. Now, thank you for your time and attention. See you in the next tutorial.